Today, I'm going to be talking about the challenges of reliability predictions in equipment working past its planned design life. I work in the oil and gas industry, and more specifically in the subsea sector. The equipment I worry about is based on the seabed, in water often exceeding 1,000 meters in depth. Typically, design lives are over 25 years. Equipment is often very difficult to get at once it's been installed. Because of this, the reliability processes tend to focus on design for reliability rather than maintenance. The strong focus on early life reliability following historic problems when the subsea industry was in its infancy. Because it's not unusual to find additional resources close to existing development, the desire to reuse existing equipment is not a new challenge, but it is a growing one. So why now? Well, the main driver is around the rapid development of carbon transition projects in recent years, and more generally, cost challenges associated with the industry. So what do we mean by carbon transition technologies? Well, two obvious examples are carbon capture and storage and offshore floating wind, two examples that are relevant for my area. Why is it that these are pushing the situation and drive to be able to understand and try and use equipment beyond its design life? Well, firstly, recycling existing equipment is just generally good. If we can avoid having to make new equipment, it's a pretty easy to understand argument that that's good for everybody. Secondly, linked to that is a lower capital cost. If we haven't got to buy new equipment, we don't have capital cost associated with that equipment. And finally, and quite importantly, is what we call our scope 2-3 emissions. So these are those emissions associated with capital equipment. Just a very brief overview on what we mean by scope emissions. So scope 1 emissions are all direct emissions for activities of an organisation under their control. Scope 2 are indirect emissions from energy purchased and used by the organisation. And particularly important in this case, Scope 3 are all other indirect emissions. So these are from the activities of the organisation occurring from sources that they do not own or control. And they're usually the greatest share of our carbon footprint. And particularly those include, Scope 3 includes the capital cost. So if we're buying new equipment, that will come in as a Scope 3 emission. Hence the importance if we can avoid using it. So typical examples of equipment we might look to reuse a lot more now than in the past are pipeline systems and platforms. If we look at the diagram on the right-hand side, each of those blue dots represents an existing platform in the North Sea. Each of the lines, particularly the green and yellow ones, which represent gas and condensate lines, are pipelines. So you can see, hopefully, that there is a lot of potential for reuse of equipment in the North Sea. And you will see a similar picture if we were looking at the Gulf of Mexico, the Norwegian sector, and other parts of the world where there's a mature subsea industry. So typically, reliability of a component is represented by what we call a bathtub curve, and you can see a simple diagram indicating that on the right-hand side, with time on the x-axis and probability of failure on the y-axis. The planned design life of a part, Tx, would typically be a point on the right-hand upward wear-out curve. But given we're talking about probabilities here, it's clear that we're all going to have examples with equipment working beyond its planned design life. So just because it's hit the design life doesn't mean it's going to fail the following day. It's all probabilities. So what drives those probabilities? Well, conservatism in design. So in the early days of the subsea industry, we weren't clear on what the environmental challenges and operational challenges were going to be. So there was a lot of conservatism built into the design. You could say it was over-designed, but we didn't know that then. There's an element of simple luck because we're talking about probabilities. And importantly as well, usage may not be as expected. So it may be that the fluids were less aggressive than predicted. It may be the pressures were lower or the temperatures were lower than expected. So there's been less wear on the equipment. The important point, though, is that our historic ability to reuse equipment beyond its planned design life may not apply as well for equipment that is reaching the end of its life today. And the reason for this is that the conservatisms in design that we built into the early equipment have largely been removed through our better understanding of how they're going to be used, through approaches like supplier-led solutions, and actually just adopting less conservative technology. So for instance, in terms of electronics, moving from military parts to COTS parts. Now, what this all drives us to is needing to find a better way, a more structured way to assess remnant life, i.e. the usable life left in a component. That's what we mean by remnant life. And this could be driven by maintenance cost, when it just becomes too expensive to maintain, particular issue for us with subsea because of the cost of maintaining equipment on the seabed is generally prohibitive. Safety, it may simply not be safe to use any longer, so clearly we can't use it any further. Or it may be due to legislative changes. So it may be that legislative changes mean that we're no longer allowed to use it because of materials or processes it uses. So how might we look to assess remnant life? What are the options? Well, to start with, let's be clear on what we're talking about here. We're talking about using equipment beyond its planned design life. So straight away, we can say that the classic approaches, such as Weibull analysis, are going to be problematic because they're all focused on that flat part of the curve that we saw earlier on. An academic review of what's available shows that actually work in this area is quite limited. And it's generally around areas that we can easily assess physical wear. So that might be boilers, it might be pressure vessels, are the two sort of classic areas you'll find that people have written on and processes exist. And these are typically suggesting the use of quantitative based check sheets and industry codes. So is the equipment still within the industry code for that bit of equipment? Generally, they assume good physical access is also possible. They also recognize, however, that while physical access and an inspection is important, operational knowledge is also key. So this is not just assumed knowledge of how the equipment has been used during its planned life, but actually knowledge with supporting evidence is the key piece there. What we find, though, is less work has been done on equipment without obvious wear patterns and where it's difficult to inspect physically. Unfortunately, this describes a lot of the subsea equipment I'm interested in. Taking all this together, though, there is general agreement that a combination of historical analysis and direct post-service evaluation should be the goal of any assessment process. So let's look at possible elements of a structured approach we can apply then across a wide range of equipment. Okay, so let's look at a method we can apply generally. I'm going to suggest we look at a 6-element approach using qualitative rather than quantitative methods. So the first element is to be clear on the new application, its risks and unknowns. This is essential. We have to know how the planned, we have to know all about the planned new use. We have to understand, as the second element, the original equipment's design premises, so its original functional design. But within that, we also have to recognize and investigate whether any concessions were agreed that could invalidate part of that functional design basis. The third element is good historic knowledge of the operation. And this is key where physical access is limited, which I've said before is typically a problem I face. So what are we talking about good historic knowledge of operation? Well, was it overstressed or damaged at any stage during its operational life? So we've seen situations with subsea equipment that's been hit by submarines. It's been dragged by trawl anchors, that sort of thing. That should be recorded and we need to understand it because that will play into really how good the equipment still is for extended life. What's its in-service history? So did it actually reach the end of its planned life or was it taken out of service early, because that could mean we've actually got some planned design life left. But taking that, how was it preserved when it was taken out of use? Can we assume, is it safe to assume, that actually its design life didn't continue to be eroded once it had been taken out of service? If it wasn't preserved correctly, this could be the case. We could see continuing corrosion. So we have to understand, what was the preservation process? Is there a decommissioning report we can review? Fourthly, are there similar systems that we can use to benchmark? This is a very powerful technique and very important, but only if they are similar. So we have to be absolutely clear they're similar. As I've said earlier on, if we're looking at older systems, they may have a lot more conservative design, so they may not be suitable to use as a benchmark. So good if we can find one, but not always available. Fifthly, we need to recognize that even physical access, limited physical access, is important and yields useful data. So what can we do if we've got limited physical access? Well, firstly, use historic knowledge to try and direct physical evaluation. So if we believe there's been an anchor drag, let's focus on the area where we believe that drag occurred, if it's a pipeline, for instance, or a bit of manifold equipment. Is there new technology that can help? So for instance, we may not be able to see the inside of the equipment, but these days we can easily put down autonomous underwater vehicles that can carry out external surveys that go far beyond just visual surveys. They can actually penetrate using sensors the actual surface of the equipment below insulation, below mud, to see what's there. So there's stuff we can do with new technology that may help us, even when physical access is limited. So the final stage, part 6, once we've completed the data gathering, is to go through a sense-making process to develop a qualitative risk-based view of the remnant life. So this is going to be looking at positives. Was it used for less than its design life? That's going to help us. And negatives, was it poorly preserved? Was it stressed? Did it suffer a collision at some stage? Importantly, throughout this whole piece, we need to be aware of quantitative results. If we've got good quantitative data, that's great, we should use it. But if we don't, we need to be very careful with it, because people tend to read a lot more into numbers than they do feelings. And people can put too much emphasis on poor quantitative data, which can invalidate the whole process if we aren't careful. So what might this look like in a practical sense? So if we take an example, this is a simple example around a pipeline. So what do we know about this pipeline? Well, firstly, what's the application? Said that that's the key thing. Well, it's a new application. We're only looking to extend its design life by about 5 years. Now, obviously that depends, that 5 years, you've got to know the context, as we'll get into in the original design. Is that a long extension or a short extension? Typically for me, that would be a short extension, but it's important to check. We also know that there are going to be no aggressive chemicals. So we're not looking to put any more aggressive chemicals through the pipeline than it saw in its original planned use. And we expect those chemicals to put there at a lower pressure than its original design basis. So what about the original design? Well, we know it wasn't designed for sour use, so no hydrogen sulfide in this case. Now that's good, because that actually matches the fact that we're not going to put any aggressive chemicals. So we're not adding to the risk there by trying to put something through the pipe that it wasn't designed for. So what is the usage history? Well, we've got no records of any excursions from the design base, so we don't believe from the evidence we've reviewed that there are any pressure excursions that could be quite significant that would impact extending the design life. We don't believe there's been any external damage. In terms of in-service history, well, the pipeline is actually, in this example, still in operation, and we expect it to be operated to its original planned design life. So it's not going to finish its use early, but it's actually still in operation now. So we know it's still working. So the next question in terms of preservation doesn't apply, which is quite a positive. It's still in service. So we haven't got any concerns around the preservation process. So benchmarks, are there any relevant equivalents? Well, we don't believe there are in this case. In terms of post-service evaluation, well, we haven't finished using it yet, so those aren't immediately available, but we do know that it's going to be highly problematic to access the internals of the pipeline, but we will be able to carry out an external AUV survey. And that'll allow us to validate the external damage that we believe they believe there isn't any. So what can we map that all onto? We can map this onto, one simple way of doing this is through something called a flying brick diagram. And this allows us to articulate visually the likely changes in risk based on the input data. So in simple terms, red bricks are bad, green bricks are good. So each red brick builds up the risk, each green brick reduces the risk. So we know it's going to be operated to the end of its planned design life. So that's increasing the risk. There's no immediate spare design life available. That said, all taken into account, we're only looking for a limited extension to the field life. We're not looking for a long extension. So that's a positive. That brings us down a little bit in terms of risk. No benchmarks, so that's a negative again. It would be good if we had something we could benchmark again, but we haven't. So that's building up the risk. Also, we're going to have limited opportunities for physical inspection. So we might have to do something on the external with AUV, but we're not going to be able to look internal to the pipe to look at internal wear and issues around that. That said, we've got a full operational history, made slightly easier here because it's still in service. So the operational data is still live. So that's putting us in a better place. And then finally, the proposed use is a significantly low design pressure. Now for a pipeline, that is a key element that is lower, and that will very directly affect our design life because that's one of the design drivers in the original design life of the equipment. So the fact we're not looking to push it to its original design pressure is a distinct positive. So all in all, quick visual review. What does that tell us? So no numbers, importantly, but it tells us, yeah, the risk is going to be increased. There is going to be an increase of risk, but actually it's going to be relatively manageable. It's not that significant. If you can kind of almost block out all the items in the middle and say that it's going to be a combination of operating it to its planned design life against the fact that we're looking to extend its use, but at a lower pressure. So that's just a really simple example of how you can do assess remnant life in a qualitative manner. And that could be applied both to items where there is physical evidence of wear and items where there isn't physical evidence of wear. So hopefully you found that useful. So to conclude then, existing reliability lifetime assessment processes are of limited value. Existing established process is also limited, particularly where there are no clear wear mechanisms. There may actually be little you can do in terms of extending design life if the main drivers are around legislative change. So I've not spoken extensively about that, but that is something often you can't do anything about, and that just means that you have to take the equipment out of life. So it's worth being clear up front that there's no legislative drivers that could cause problems. Post-service inspection, while important, needs to be backed up by in-service inspection. So how was it maintained? Was it stressed at any point? And that needs to be good historical knowledge. That's what's key, not assumed knowledge. So I don't remember there ever being any problems. Actually, a review of logs, they almost certainly are available. Most stuff is kept for good reasons, certainly in my industry. So put the effort into reviewing those. Now, that may be something that we can look to automate through AI processes these days, but one way or another, we need to go through and assess all the historical logs to confirm, Tom's view that actually it was fine. That doesn't really work. We need good evidence. And then finally, key point, really be careful around qualitative versus quantitative. Trying to apply numbers, particularly where there's no clear evidence of wear, there are no governing industry codes that are used for assessing remnant life, is a high risk. People put too much emphasis on numbers and will believe them if they see them. So they're in some ways best avoided at something like this. Okay, so that's all I want to say today. Thank you for listening, and I'd like to ask if there are any questions.